So today we're going to look at fission and fusion and some other positive aspects of nuclear chemistry. So here we see fission is when we split a nucleus into smaller fragments. And we start with our larger atoms, our trans-uranium elements. They're very big, and when we split them into smaller parts, we get a lot of energy that is released from the splitting of those atoms. This is different than decay. Decay, or unstable nucleus, releases particles in an effort to become stable. Here we actually start with neutron bombardment in an effort to get the atoms to split. And so here you can see in this image, if a neutron strikes a uranium nucleus right here, then it's going to split into a krypton nucleus and a barium nucleus. At the same time, some extra neutrons are going to come out. And now these neutrons are available to strike other uranium atoms. And when that happens, again, more neutrons are released, striking more uranium atoms, and we get what's called a chain reaction. And so when this chain reaction occurs, we can get a lot of energy coming out of a radioactive source, like uranium, a large nucleus. Now, if we want the reaction to keep going, then we need to have a critical mass of uranium available, or plutonium. And when this is happening, that we're talking about like a nuclear power plant, like down the road in Perry. If we don't want it to keep going, if we just want one burst of energy, then we don't need to have a critical mass. We're just going to need a very small amount of fissionable material, as we'll see. And when that happens, we have an atomic bomb explosion. Let's look at the nuclear power plants first. Here's a little diagram of how they work, which I think is important, especially since we live so close to one. But any electricity generating plant is going to be near the water, because essentially we need to turn water into steam. And once we do that, that steam turns a turbine, which is attached to a generator, which creates an electric current. So when the water comes in, if we heat it up with a nuclear reaction in the reactor, well, that's fine. We can also heat that water up and turn it to steam using coal, which is what's happening down the road the other way in Eastlake. But either way, we cause the water to turn to steam and we get an electric current generated. So let's look at some aspects. We'll focus here at where the nuclear reaction is: control rods and fuel rods. Perry power plant is an example of a light water nuclear reactor. And we control the chain reaction by inserting control rods into the fuel rods. These control rods absorb neutrons. So if the neutrons aren't able to go hit more uranium atoms, then we control the chain reaction. And so if the control rods are fully inserted, then we have a complete shutdown of the reactor core. And as you start to pull the control rods out, then the chain reaction goes and we generate the heat and create the electricity. If you pull out too many control rods, we can have a meltdown. And this is what happened in our world's worst nuclear power plant disaster in Chernobyl in 1986. You can do a little research on that if you'd like online. It was bad, but again, compared to other disasters we've seen around the world, the death toll was not that high. There has been not a single fatality in the United States due to nuclear power. Now, why do we pursue nuclear power? Okay, and it's right here. Down the road, when we burn 3 tons of coal to generate electricity in Eastlake, we get the same amount of electricity from 1 gram of uranium over in Perry. 1 gram is like the mass of your pinky fingernail. So a heck of a lot less fuel is used to create that electricity. Over in Eastlake, when they burn coal, we release carbon dioxide, which contributes to global warming. We also have other pollutants coming out. With Perry, when you look and you see that huge plume coming out of the cooling tower, that's just steam, that's just water. The big downside, of course, to nuclear power is the radioactive waste that is created. We have to find a place to put it and store it, etc. And Mr. Bill Nye will talk about that with us in class in a couple days. So I'll save that for him. So again, fission, start with big atoms, split them apart, get a lot of energy. And radiation. Fusion is the opposite. Okay, fusion, we combine two nuclei and we produce a heavier nucleus. So we're going to start small. Like in our sun. Our sun, hydrogen nuclei fuse together and form helium. Helium is much more stable, so the extra energy comes towards planet Earth and allows us to sustain life here, and we're happy about that. Now, in order for this to happen, we need a tremendous amount of pressure and a very high temperature, 15 million degrees Celsius. And I mentioned to you before that our sun is dying. It's a cold plasma, but even still, 15 million degrees Celsius is unable to be housed here on planet Earth. And so sustainable fusion as an electricity source is just not possible, at least that type of fusion. What we're trying to do is what's called cold fusion, where we move the particles so fast that when they smash together, they stay together. Well, that's how we make a lot of our transuranium elements. But in order to use hydrogen, which would be totally awesome, because we'd have an unlimited fuel source. That's what we're trying to do. That's what we're trying to work on to get, viable electricity source out of cold fusion of hydrogen. Right now, these cyclotrons and stuff have to be housed under these huge magnetic fields, and we're putting in way more energy than we're getting out. So it's just not viable yet. And so that's why we're still pursuing, because wow, how awesome would it be to use hydrogen, and it's all around us, but not quite possible yet. So there definitely are dangers involved with nuclear chemistry, especially radiation, but there's a lot of helpful ways besides power plants that nuclear information and science can be used. For example, you might have a smoke detector at home. If you do, you have radioactive americium, and that americium emits alpha particles, which, if you remember, they are large in the world of particles, so they can't penetrate your skin. They can't harm you, damage that way. And this americium will be radioactive for decades, so as long as you maintain and change the batteries of your smoke detectors, they'll work for a very long time. And you can see, I put in your notes packet, essentially what's going on is an electric current is created because the alpha particles knock electrons off of the oxygen and nitrogen in the air around us. And if smoke enters in, well, then that electric current is disrupted and the alarm goes off. So that's one example of positive nuclear. Probably even more importantly in the medical field, unbelievable advancements courtesy of nuclear science. And not too long ago, a little over 100 years ago, if something was wrong inside of you, they had to cut you open and look around, and then staple you, stitch you back up, and hope that you didn't get an infection. Well, then the x-rays came along, and those are great, especially for bones and a little bit of soft tissue stuff. But nowadays, all of these different imaging radioisotopes we can use, even barium too, that you can swallow, whether it be injected or swallowed. It's fascinating, the images that we can see, and like the capillaries in your circulatory system or the neurons firing in your brain. Here's an example of a PET scan. This is an image of a person that got a PET scan, and unfortunately they have bladder cancer, and you can see that it's showing up on this PET scan. There's other normal activity that shows up, but a radiation tech and a doctor would be able to instantly see those images and realize that this person has a tumor in their bladder. Or perhaps the imaging of your heart using thallium. And again, a nuclear tech, you could see, looking at these images, like how's your ventricle operating, or is there any compromised blood flow, is there blockage, etc. So just fascinating stuff courtesy of nuclear science as far as medicine is concerned. And we're going to see a video detailing more of that coming up as well. Now, if you do work around radiation, typically you have to monitor your exposure, with a film badge, because you can't see radiation, can't hear it, can't smell it, can't touch it, can't taste it. And so the only way to know if you're getting exposed to too much is by checking on how much you are being exposed to with like a film badge. Now for this chart, I just wanted you to write the symbols the abbreviations for the different units of radiation measurement, and partly just to note that a lot of these reflect pioneers in the nuclear science field. I'm sure you might have heard of Marie and Pierre Curie. People that worked with nuclear stuff, radiation, died very young because they didn't know that what they were being exposed to could cause serious consequences like cancers. So Becquerel, that was another pioneer, French scientist pioneering in the field. Röntgen, that's who invented the X-ray. So the next time you're getting an X-ray, you can probably see on the device how many Röntgens are being emitted per exposure. Rad, like that article, Life is Rad, and in that article, it kept talking about rems of exposure. Technically, though, it was talking about millirems. So when we look at this next chart, where I want you to note the dosage, it's all in rems. So if you remember from that article, the average American is exposed to about 600 millirems of radiation. And a millirem, there's 1,000 millirems in one rem. So 600 millirems is less than 1 rem. So you can see up to 25 rems, there's no observable effect, which means up to 25,000 millirems. After that, if you've ever known someone that might have been going through radiation therapy for cancer, you can see some of the side effects here. People that are getting that treatment have a compromised immune system. The white blood cell count is low, so they're very susceptible to colds, flus, etc. They could lose their hair. They can be very nauseous, so a lot of anti-nausea medication is tied in with radiation treatment. And so that's how you can see that they're being exposed to a higher than normal dose of radiation. Down here, we're talking about, near an atomic bomb blast or a nuclear power plant meltdown. Again, hopefully we never have to see anyone suffer from that on this planet in the future, but that's what we're talking about there. Our last little notes, besides a film badge, we can use other devices to detect radiation, like a Geiger counter. You may have seen or heard one of those. They beep or click in movies. Or a dosimeter. They altered one in Ghostbusters to detect the paranormal spirits. And we'll see a couple more examples of these next year in that other nuclear video, but that's another way that we can detect radiation, radioactivity in our environment. So that's it. I hope you had a fantastic experience on this video and all year, but if you get a chance, you can check up on YouTube and see some atomic bomb explosions. There were a ton of practice bombs that were detonated before we actually dropped a bomb on Hiroshima, and they're quite spectacular to view. This video, if you look for it, if you want to search on YouTube nuclear bomb explosions, or you can see this website right here if you want to type that in, then you can see there's quite an impressive display of a bunch of different atomic bomb detonations. So, alright, have a good one, and I'll see you another time.